Okay, g'day students, and welcome to our first lesson on acids and bases. So we're back on acids and bases, and we're moving on from the Arrhenius model of acids and bases, and we're going to look at the Bronsted-Lowry model of acids and bases today. So today we want you to be able to recognise the relationship between acids and bases and equilibrium systems can be explained by the Bronsted-Lowry model, and represented by using chemical equations that illustrate the transfer of hydrogen ions, which are protons, between the conjugate acid and base pairs. You should be able to recognise that the amphiprotic species can act as Bronsted-Lowry acids and bases, and identify and deduce a formula of conjugate acid or base of any Bronsted-Lowry base or acid. So let's have a look at the definition. So Bronsted and Lowry defines an acid as the proton donor and the base as the hydrogen ion or the proton acceptor. So if we have a look at this reaction down below, we've got ammonia in water and it dissociates to form ammonium and hydroxide ions. And what's happening? Can you see what's happening to the hydrogen ion? You can see that water here, let's get a darker colour pen, has donated a hydrogen ion to the ammonium. So ammonia is the hydrogen ion acceptor. So this is ammonium. It's accepted a hydrogen ion, and this is the base, and this is the conjugate acid. So if we have a look here, we can see that we have a base and a conjugate acid. So we've got a conjugate acid-base pair there, the ammonia and the ammonium. The water in this case acts as an acid because it is donating the hydrogen ion or the proton, and hydroxide over on the right hand side becomes the conjugate base of the acid. So our conjugate acid is a particle formed when the base gains a hydrogen ion. So ammonium is the conjugate acid of the base ammonia. The conjugate base is the particle that remains when an acid has donated a hydrogen ion. So hydroxide is a conjugate base of the acid water. And the conjugate acid-base pair are two substances that are related by the loss or gain of a single hydrogen ion. So ammonia and the ammonium ion are a conjugate acid-base pair. Let's have a look at this one. We've got hydrochloric acid or hydrogen chloride in water. So Bronsted-Lowry, remember, defines the acid as the proton donor and the base as the proton acceptor. Now the hydronium ion, remember, is the positive ion formed when the water molecule gains that proton. And we should recall that water is amphiteric. That means it can act as both as an acid as a base, as we'll see here. So what's happening? Can you see hydrogen chloride? Here's hydrogen chloride, it has donated a hydrogen to the hydronium, it has donated a hydrogen to the water to form a hydronium ion. So our hydrogen chloride is our acid, and our conjugate base of that is that particle that remains, which is the chloride ion. That means the other two are the other pair there. So the water is the base in this case, and the hydronium ion is the conjugate acid. So if we have a look at the diagram on the right hand side here, we can see that hydrochloric acid donates hydrogen to form the chloride ion. We've got sulfuric acid, nitric acid, hydronium. The next one is ethanoic acid, and so on. So we've got a few acids and base pairs here for you just to have a look over. Now, you should also remember that hydrogen ions come from water. So remember that in pure water, hydronium ions and hydroxide ions are being formed. Now, that's quite a very low level. And at the same time, those water molecules are being reformed. So we've got the hydronium and hydroxides reforming to form water, and then there's that equilibrium. So the point of this slide is that just to help remember that water is amphiteric. It's a substance that can act as both an acid and a base, and that's because water is amphiprotic. amphiprotic. It can accept or donate protons. So acids can donate protons, and we're going to look at what we call polyprotic acids. So poly meaning more than one, and protic meaning that they can donate more than one proton. So if we have a look at the top right hand corner, you can quickly tell hydrochloric acid can donate one hydrogen, nitric acid can donate one hydrogen, sulfuric acid should be able to donate 2, phosphoric acid should be able to donate 3. Now ethanoic acid will only be able to donate that hydrogen on that end. The rest is an ethanoate molecule. Now sometimes we call that acetic acid and the remaining molecule acetate. Now carbonic acid should be able to donate 2 hydrogen ions. So if we have a look at monoprotic acids, for example hydrochloric acid, nitric acid and ethanoic acid, they will just donate 1 hydrogen ion. Now diprotic acids are any acids that contain 2 ionizable protons. So remember they're hydrogen ions, such as sulfuric acid or carbonic acid. And so we have 2 stages of dissociation with diprotic acids. The first step is when, for example, we have sulfuric acid and in water it's going to donate 1 hydrogen ion to form this HSO4 minus. Now HSO4 minus is a weak acid and it only partially dissociates, and we've got this 2 ways arrow indicating that it's an incomplete reaction. So it can go on and further donate another hydrogen ion, or it can accept another hydrogen ion. So we say it's amphiprotic, and that means it can act as an acid or a base depending on whether it's accepting or donating hydrogen ions. So this is when we're looking at stage 2. So we've got here sulfurous acid plus water will leave a sulfate ion, it's SO4 2 minus, and the hydronium. So there's 2 stages of dissociation for diprotic acids. And we should note that in a solution of H2SO4, we'll have very little H2SO4 molecules, and that's indicated by the forwards arrow. It pretty well dissociates all its protons, or it ionizes quite well, and the solution of H2SO4 will contain then hydrogen ions, or hydronium if you want, HSO4 minus ions and SO4 2 minus ions. Now triprotic acids are any of those acids that contain 3 ionizable protons, and recall that's this one here. We've got a H3PO4. So we just have 3 stages of dissociation, and so you can see that each step we are losing a hydrogen ion. So we're going from H3PO4 to H2PO4 minus, and then we're going in stage 2, we've got the H2 down to just 1 hydrogen. So H2PO4 minus will become HPO4 2 minus, and then, whoops, I should colour that in, and that should only be, no, that's right. Yeah, we should only have 1 hydrogen ion there, sorry. And then that will dissociate to form the phosphate molecule, which is PO4 3 minus, and hydronium ions. So can you recognise the relationship between acids and bases, and equilibrium systems can be recognised or explained by the Bronsted-Lowry model. We can use those chemical equations to illustrate the transfer of hydrogen ions, protons, between those conjugate acid-base pairs, and recognise that the amphiprotic species can act as Bronsted-Lowry acids and bases, and identify and deduce the formula of the conjugate acid or base of any Bronsted-Lowry base or acid. When you've done that, have a go at the mastery exercises, please.